Hi there. I will be conducting a full series of videos on the subject of multivariable calculus. This is the first introductory video in that series. It's just going to focus on introducing functions of several variables. Thus far, in your study of calculus, many people would have been introduced to just studying functions of one variable. That is, y would be a function of x. Y is the dependent variable and x is the independent variable. We would have some quantity or some phenomena y that would just be dependent on one single thing. An example of this could be perhaps the growth of a tree. We could have a tree that's 1 year old and has a particular size. We could have another tree that's 5 years old and it could be substantially bigger because it's older. So what we're saying is that the height of the tree or the size of the tree just depends on the age of the tree. We could write h as just being a function of t. But in the real world, it's rare that we would have or we would find quantities of phenomena that just depend on one single thing. If we think about the complex world around us, we can easily see that we have to think of many factors. An illustration of this would be, of course, the weather. If we were to determine the amount of rain that is going to occur on any given day, what would we have to think of? Well, we may have to consider the air temperature. We could perhaps even think of the air pressure, the humidity in the air, that is the amount of water vapor in the air. We could also probably think about maybe the wind speed. We could think of the geography of the land. We could think of the ocean currents. There's probably a million different types of variables that we could consider in trying to predict the amount of rain that is going to happen in any given day. There's hundreds of variables, and some of these variables may even depend on each other. Even with this example of the tree that we considered earlier, we did reduce this to one single variable by making a number of factors to remain the same. For example, maybe the type of tree, the species of the tree, maybe the area in which it was planted, the amount of minerals in the soil, maybe the amount of water that both trees were given. So we kept all of those constant and just only considered the age of the tree. So in other words, we considered that the tree was the same type, it was in the same place, etc. So how do we now extend our knowledge of calculus to consider more than one variable? So calculus has been focused on considering how does, for example, the height of the tree change with time. So we now need to extend that thinking into more than one variable. And the easiest way to do it would just be to consider, instead of one variable, two variables. We would create a new variable or a new dependent variable z that's now dependent on two independent variables, x and y. A simple illustration of this that you would have seen is the area of a rectangle. The area of the rectangle depends on the length and the breadth. So what we could do is just create a variable z, and it is the product of the length, which we can call x, and the breadth y. So we have z is equal to xy. This is now a function of two independent variables. So the question now is, how do we draw this? How do we think about it? How do we plot it? What does it look like? And that sort of thing. Because when we had one independent variable, we just had a two-dimensional graph. We plotted y and x, and maybe there would be some curves that we could consider, a linear curve or a quadratic curve, etc. So what does three variables look like? That is one dependent and two independent variables. So these z values, they are a vector of values. They can go from minus infinity to infinity. In this example, we're considering the area. So the area has to be greater than 0. So the starting point would be 0, 1, 2, 3, etc. And now on the right-hand side, we have xy. So what does xy mean? Well, we're now considering a matrix of values. The rows of this matrix would be the x values and the columns would be the y values. So in the first row, we could have x equal to 0, y equal to 0, then x equal to 0, y equal to 1, x equal to 0, y equal to 2, and so on. And in the second column, we could have x equal to 1, y equal to 0, x equal to 1, y equal to 1, x equal to 1, y equal 2, and it will carry on like that. So if we were to draw this graph, what's going to happen is that it's going to be a 3D plot. So it would be an object, it would be a shape, and it's difficult to draw these kinds of diagrams, do these kind of plots. So they are software that people would normally go to, and you could just do a simple search for it, and it would come up. You would just put in your equation, z is equal to xy, and then you would have an idea of what it would look like. And in this instance here, it looks something like this, where we have our z values, which we can see on the left-hand side, and we have our base consisting of x and y. So that would be this matrix of values here forming the base, and then the third axis coming out of the page is the z-axis. Another example in which we could think about, in that we could try to actually draw, is the function maybe z is equal to x squared plus y squared. What does this function represent? What would it look like in terms of a 3D plot? One technique or one strategy that can be employed into trying to plot a 3D graph like this is to consider the various planes. So if we were to draw these axes, we would have a third axis, the z-axis. We could have a y-axis, and we would of course have the x-axis. So the strategy is to think about what would this plot look like in the various planes, and plot the graph based upon what it would look like in the various planes. So when we speak about the xz plane, we're speaking about the plane that runs something like that. If we speak about the xy plane, or the zy plane, we're talking about the plane that runs like that. So if we were to put these different variables to 0, that is x and y, and try and figure out what it looks like in the various planes, we might be able to plot it. So if we set x equal to 0, then we get z is equal to y squared, and this is just a two-dimensional graph, and it's a parabola, and of course it looks something like that. And if we do the same with x, that is set y is equal to 0, we're left with z is equal to x squared. That's z and that's y. And now if we plot z and x, we are left with the same thing. So what we're saying is that on the zx plane, the graph looks something like that, and then it continues on into 3 dimensions. And on the zy plane, it also looks something like the parabola. So if we were to complete this graph, we would draw a circle like that, and that would be what this graph would look like. It kind of looks like a champagne glass. And if we put this plot in our software that we can run online, then we see that it looks something like this, which is kind of what we had come up with this as well. So another important point that we can use to conclude this video is we can now cut this graph in different planes. We could cut it there, we could cut it there, and we could cut it at each of these different points. That is, if we look at it from the top and we were to cut out chunks of it in the manner in which I've drawn it, what would it look like? If we draw, that is the projection on the xy plane, that is, we're drawing the base xy, and we're looking at it at the top, what are we seeing? At the point of origin, we're just seeing a dot, okay? And then as we go up the z-axis, we're seeing different values of z in which circles appear. If we look at it at the top, we just see a circle, and if we cut it off at different points, we will see smaller circles until it's 0 at the origin. So we see a series of concentric circles if we were to look at it at the top. So what these are called are level curves. So these play an important role in the topics that we will consider in previous videos, or sorry, in the upcoming videos. So to summarize this video thus far, what we have considered is functions of multiple variables. We saw that calculus simply depends on one variable at the start in which we study it, we see that the world consists of many variables. We now have to extend our study to more than one variable. So we consider two variables. We create a new dependent variable z, which is dependent on x and y, which are the new independent variables. We see that our base is the x and y axis, which is a matrix of values, and we get a single output z. And thereafter, if we were to try and plot different values or functions of multiple variables, we can consider different planes, what it would look like in different planes, and then try and figure out what it would look like in 3 dimensions. And we can verify this by using online software to get an indication. We can then look at the projection of the graph at different values of z on the xy plane. And in the example that we considered, z is equal to x squared plus y squared, we see that we see a series of concentric curves. These are called level curves. In this video, we're going to look at derivatives of multivariable functions. If we consider z to be a function of x and y, the question is then, what is the derivative of z, or what is the rate of change of z? If we have a 3D plot, how does z change in terms of 3D? Well, what happens is that we consider z in terms of the rate of change with respect to each individual variable. In other words, we would have the rate of change of z with respect to x and with respect to y. So you can see that we have used the notation day. So this means that the derivative is taken with respect to a single variable, but in a multivariable function. Whereas dy dx was the derivative of a single variable function, day represents the derivative of a function of one variable, but in a multivariable function. We can also have second derivatives. So we would take the first derivative and take the derivative of it again. And we would do the same of the other variable. We can also take this first derivative and then do it with respect to y. So we will be taking the derivative with respect to y of day z dx. So what this looks like is the second derivative of z that was initially taken with x and taken of y. And the same would be done with respect to x. So we would find the derivative of x of day z dy. And this would be the second derivative of z, initially taken with y and taken with x now. So these are called mixed partials. As a general rule, we expect the mixed partials to be equal. So that is day squared z dx dy is equal to day squared z dy dx. In terms of an example, we could look at z is equal to x squared plus y squared. The derivative of z with respect to x is simply 2x. We treat y as a constant, and the derivative of a constant is equal to 0. In this case, y squared is seen as a constant, and therefore its derivative is 0. And then we would do the same with respect to y. So day z dy is simply equal to 2y. In this instance, we have treated x as the constant. So x squared is just a constant number, and its derivative is equal to 0. That's why day z dy is equal to just 2y. We have taken the derivative of y squared. So what does this mean geometrically? Well, if we plot the function z is equal to x squared plus y squared in 3 dimensions, so please excuse my poor drawing. We see that this function looks as a champagne glass, which is what we've discovered in the last video. So if we're saying that y is equal to a constant, right? What are we saying? Well, we can choose any value of y. Let's just say y is equal to 2. and we take a slice, or we take a snapshot of this function where y is equal to 2. So what would that look like? It would look something like this. We take a slice at 2 and we cut it out of the graph. So imagine now we're taking like a little saw and just extracting out what the graph looks like where y is equal to 2. So imagine that this graph is being cut out at y is equal to 2. There's y is equal to 2 here. And it's being cut at that point. This entire little slice is taken out. And then if you plot that slice, right? So we plot that little slice. What does it look like? Well, it's a plot of the xz plane. You can see that this is z and this is x, and that little slice is the xz plane. So we have x and we have z. What this looks like, what it would look like if we were to take a slice, is that it's a parabola. And we have chosen the value y is equal to 2. What that looks like in terms of the equation is that z is equal to x squared plus 4, because the equation is y squared and 2 squared is 4, so z is equal to x squared plus 4. And this is very familiar because this is what a parabola is, which is very well studied in earlier courses of maths. So the question is, day z, day x, what are we saying here? We're saying that it's equal to 2x. We're saying that on this specific plane with this constant variable of y, we're saying that this is how z changes with x. Z changes with x linearly, 2x. So this is how z changes with x. So that's what we mean when we say we keep the variable y constant. So if we take day z, day y, what we're doing is we're making x constant. So we're choosing a value of x. We can choose a value of x here. Again, we can choose the value 2, and then we take a snapshot of it. And for each snapshot, we will have, this is how z changes with y, or in the instance of x, this is how z changes with x. So if we continue with this example, then we can take the second derivative, day squared z, day x squared, and if we find the second derivative, we see that this is just equal to 2. Of course, the derivative of x is just 1. And then we find the derivative of z with respect to y, and that's equal to 2 as well. And then if we take this derivative and then find the derivative of that with respect to y, in other words, we find the mixed partial, day squared z, day x, day y. So the derivative of this with respect to y is just going to be 0 because there is no y in this function. It's just x, and x is being taken as a constant. And if we do the same, with the mixed partial, where we take the derivative of z, day z, day y, and then find it with x, we find that this is 0 as well because there is no x inside this equation, and therefore y is taken as a constant, so this is 0. And we see that these both are equal, which is what we said is the case very generally. Yeah. In this video, we're going to look at derivatives of a more complicated multivariable function, and in the process, we're going to revise the chain rule and the product rule. So let's start off with the chain rule. What the chain rule focuses on is finding the derivative of a function inside a function. If we have a function y, which is equal to sine of x squared, how do we find the derivative of this? What the chain rule says is that we have to think about it in terms of an inside function and an outside function. So the outside function is sine, and the inside function is x squared. So the derivative of the outside function is the derivative of sine, which is cos, and we have to multiply this by the derivative of the inside function, which is the derivative of x squared, which is 2x. That's our answer. In terms of notation, what we do is we let a new variable, let's call it w, and we let that equal to the inside function, which is x squared. So what the chain rule says is that dy dx is equal to the derivative of y with respect to this new variable w multiplied by the derivative of w with respect to x. So if w is x squared, it means that y is the sine of w. So dy dw is equal to the cos of w, which is just the cos of x squared. And the derivative of w with respect to x is simply 2x. So applying this chain rule formula, dy dw is cos of x squared, and dw dx is 2x. So we can see how it is the same thing, but it's very simple and easy just to think about it in terms of an outside function and an inside function. Another example would be y is equal to e to the power x squared. So to find the derivative of this using the chain rule, we find the derivative of the outside, which is just e to the power x squared, and the derivative of the inside, which is just 2x. Okay, and that's our answer. One final example that we can look at is y is equal to e to the power sine x. As before, we find the derivative of the outside function. E to the power whatever is just e to the power whatever. So the derivative of e to the power sine x is just e to the power sine x as the outside function. We multiply this by the derivative of the inside function, which is the derivative of sine, and that is cos x. Okay, and that's our answer. So now we can move on to the product rule. So what does the product rule say? The product rule says that if we have a function that is the product of u, which is a function of x, multiplied by v as a function of x, then dy dx is equal to u times dv dx plus v du dx. An example would be y is equal to x squared sine x. So this would be u, and that would be v. So we would let u equal x squared, and we would let v equal sine x. So du dx is equal to 2x, and dv dx is equal to cos x. Applying the chain rule, what we get is dy dx is equal to, firstly, u, and u is x squared, multiplied by dv dx, and dv dx is cos x. Added to this is v, which is sine x, multiplied by du dx, and du dx is just 2x. That's how we would find the derivative using the product rule. So now we will apply this in our multivariable example. We can take the multivariable function z is equal to e to the power sine x times cos of y. So let's start off with the derivative of z with respect to y. It's pretty much easy to do this because x is a more complicated looking function. Just as a reminder, if we have y is equal to kx cubed, where k is a constant, then dy dx is just equal to 3k x squared. So the k does not change inside this particular derivative. So if we're finding the derivative with respect to y, then e to the power sine x as a constant just remains as is. So day z, day y is equal to, firstly, the constant e to the power sine x multiplied by the derivative of cos y, and the derivative of cos is minus sine. So this is fairly straightforward. Now if we find the second derivative of this, we say day squared y, day x squared. This is equal to, again, this e to the power sine x does not change, it's the constant. And the derivative of sine is cos, and of course there's a minus in front. So that is the second derivative. So now we would move on to the derivative of z with respect to x. So day z, day x is equal to, firstly, cos y remains as is. We just write that down as the constant. And then this is being multiplied by the derivative of e to the power sine x. So using the chain rule, and we had did this already, the derivative of e to the power sine x is simply the derivative of the outside function, e to the power sine x, multiplied by the derivative of the inside function, which is derivative of sine, which is just cos. Finding the second derivative, again, cos of y remains the same as it's a constant. We treat the other variables as constant. Now we need to find the derivative of e to the power sine x times cos x. So we can see that this is the product of two functions of x, so we need to use the product rule. So let's just remind ourselves what the product rule is. So it's u times dv dx plus v times du dx. In this case, u is equal to e to the power sine x, and du dx is equal to e to the power sine x cos x. V is equal to cos x. Therefore, dv dx is equal to minus sine x. Putting all of this into the equation, firstly, u is e to the power sine x, e to the power sine x, multiplied by dv dx, which is minus sine x, minus sine x, then we would add to this v is cos x, and du dx is e to the power sine x cos x. We're multiplying v by du dx. We see that there's a cos x here, and we're multiplying it by the cos x here. So this cos times this cos is going to give us cos squared. So we're going to be left with e to the power sine x multiplied by cos squared x. Okay, I would just like to move this to this side to make it look a bit better. Okay, and that's our final answer. In terms of the mixed partials, we could find day z, day y, and then with respect to x, so day squared day z, day y, then taken with respect to x. So we're finding e to the power sine x times minus sine y, and then we're finding the derivative of this equation with respect to x. So what we're going to be left with is minus sine y, since it's treated as a constant, multiplied by e to the power sine x, which is just e to the power sine x times cos x. Then finding the derivative of day z, day x, now with respect to y, it will be day z squared divided by day x taken with respect to y. So this is going to be the derivative of cos y with this kept constant. So the derivative of cos is minus sine, so we're left with minus sine y, and this is multiplied by the constant part, which is e to the power sine x times cos x. And we see that these two are equal. So we see that day squared z day x day y is equal to day squared z day y day x. So as a general rule, this is true. So in a test or in an exam, it could be asked, show that the mixed partials are equal to each other. So what we would need to do is find the first partial derivative of z with respect to x, then take the second derivative of that with respect to y, which is what we've done here, and then do the same with day z, day y, find that first, and then take that with respect to x, and then find both of them, and if they are equal, then it means that your working was correct. In this video, we're going to be looking at function differentials. We're going to be looking at the derivation of a very important relation that we're going to use in future videos. It forms a lot of the basis of the work that follows, and the relation is day z is equal to day z dx times dx plus day z dy times dy. So where does this relation come from? It can be derived in numerous ways. I think perhaps one of the most interesting ways to do it is to look at Taylor series. So we write Taylor series for this multivariable function z, and we able actually to come up with this relation. So before we start doing that, perhaps we would just do a quick revision of Taylor series. So we have a function z that depends on x and y. And if we want to have some differential change, or rather some change in z, for this change to z in z to occur, there must have been a change in x and y. So it's this change in x and y that has actually caused this change in z. So of course, the change in z is simply just the function with the changes in x and y subtracted by the original function. In other words, we take this z to the other side, and z is of course a function of x and y, so we write minus z, and z is equal to f of xy. So using this equation as the basis, we can now proceed in writing Taylor series. Let's just do a quick revision of Taylor series in one dimension. We're doing a revision of Taylor series. So what most textbooks would do is they would present it as f into x plus h. So this h is just some distance away from x, not too far away, but it's some distance away from x. So what is the function of some h distance away from x? And what it is the function at x plus h times the first derivative at x divided by 1 factorial plus h squared times the second derivative at x divided by 2 factorial, then h cubed times the third derivative at x divided by 3 factorial. So it carries on in this manner, and it can continue in that way forever. So what we're just going to do quickly at this stage is just replace some of these variables relative, because that's what we're going to use in our exercise. So we're going to replace this h with delta x and this f prime with dy dx. So we're just replacing h with delta x and just rewriting this as is. So we're just going to write dy dx multiplied by h over 1 prime, or rather delta x, plus the second derivative times delta x squared over 2 factorial. And lastly, the third derivative multiplied by delta x cubed divided by 3 factorial. So we now extend this to 2 variables. So the question is, how do we do this? How do we extend this Taylor series in 1 dimension to that in 2 dimensions? So Taylor series in 2 dimensions. So if we look at our function, we see that we have 1 variable, right? And it's the derivative with respect to 1 variable. So if we have 2 variables, x and y, all that happens is that we write the Taylor series for each variable. So for the second derivative, this is the second derivative here, we won't just have the derivative with respect to x, we'd have the derivative with respect to x and y. So we'd have the second derivative day z squared, day x squared, we would have day squared z, day y squared, and also we would have the mixed partial as well. Day z, day x, day y. And you would remember that in the previous video, we saw that there are 2 mixed partials, day z, day x, day y, and also day z, day y, day x. So what this means is that they're actually 2 mixed partials, and since they are the same, they are actually equal. So we have 2 of these mixed partials. So now we can proceed to write our Taylor series in 2 dimensions. So instead of just x plus delta x, we would have x plus delta x and y plus delta y. So x plus delta x and y plus delta y, and this is equal to f at xy, since there's 2 variables. The analogy is the same, so it's the same series but written for both variables. Then the first term, we have day z, day x, so we would write that down. Day z, day x, and we have the differential day x, 1 factorial, and we would have, for the other variable, day z, day y, delta y times 1 factorial. So now it's just a little bit more complicated when we're writing the second derivative, and how we would do it, I would just continue this here on the next line. We would say plus, okay, so we have this 2 factorial. We're going to write this entire term that you see on this top, the second derivative term, we're going to write it for each of the second derivatives. So writing this 2 factorial, just going to bring that out in the front. We're going to have firstly the second derivative with respect to x. So it's going to be dz dx squared times delta x squared plus this mixed partial, so there's two of them, 2 dz dx dy multiplied by delta x delta y, and then lastly plus d squared z dy squared delta y squared. And this is going to continue for the third derivatives and fourth derivatives and so on. Right. So can we actually refine this at some stage? So if we just do a bit more algebra here, we can take this function xy to the other side. So we have f(x) plus delta x, y plus delta y, and we move this along to the other side, becomes minus fxy, and then this is equal to all the stuff. So starting from here, we write this dz dx times delta x, that term, then plus dz dy times delta y, and plus these higher order terms. So it's dz squared dx, delta x squared, etc., etc. So when we mean higher order terms, we mean these higher order derivatives. We'll just call it plus higher order. Higher order terms. What we're going to do is start taking a limit. So when we say we're going to take a limit, we mean that, but before we even do that, if we just look at this term on the left-hand side, if we go to the top, we see that delta z is equal to f into x plus delta x, y plus delta y minus f into xy. And if we look at this term on the right-hand side, we see that it's the same as this term here, what's on the left. So this entire term on the left is just delta z. We can see it. So delta z is equal to all of the stuff on the right-hand side. That's dz dx delta x plus dz dy delta y plus these higher order terms. So we can now take the limits that I was speaking about, in which we let delta z approach dz. So a change in a small change in z, delta z, now becomes a differential change in z. That means an infinitely small change. So a small change becomes an infinitely small change. So once delta z approaches dz, delta x will approach dx, and delta y will approach dy. All these higher order terms actually cancel out. They cancel out because if we look at these terms, we see that we have a delta x squared. We see we have a delta x times delta y, and we see we have a delta y squared. So what is happening is that we have small changes being multiplied by each other. If we think of a small change, for example, 0.01, and we multiply it by itself, 0.01, a small number multiplied by a small number gives us a much smaller number. So we can imagine that if this delta x becomes dx, an infinitely small number, and we multiply it by another infinitely small number, we're going to get a number that's virtually almost zero. So all of these terms actually can become 0. So we would actually remove them. And if this is true for the second order derivatives, then it will obviously be true for the third order, fourth order, and so on. So all of these terms can be neglected. And what we're left with is that dz is equal to dz dx times dx plus dz dy dy. In this video, we're going to be looking at rates of change of multivariable functions. When we speak about rates of change, we're speaking about time. We're asking, how does something change with time? We saw in the last video that some multivariable function, or rather a change in some multivariable function, that would be delta z, is equal to dz dx multiplied by delta x, some change in x, plus dz dy multiplied by some change in y, delta y. So if I divide this entire equation by delta t, I would get delta z divided by delta t is equal to dz dx times delta x divided by delta t plus dz dy times delta y divided by delta t. If I then let delta t approach 0, what I'm going to get is that dz dt will approach dz dt. So dz dt is equal to dz dx times dx dt plus dz dy times dy dt. What does this equation mean? What this equation means is that if I have some variable z, which is a function of x and y, and if I want to understand how does this variable change with time, well, I would say that it's equal to the rate of change of z with respect to x multiplied by how x changes with time plus the rate of change of z with respect to y multiplied by how y changes with time. So if we were to look at an example, and this example could be a cone. We have a cone. The cone has some radius. There's the center, the base of the cone, and it has some radius, and it has some kind of height. So this has a volume, okay? It has a volume. And the question would be, how is the volume changing if we were to change one of these variables? Let's just say, for example, the radius is changing. The radius is getting bigger. If the radius is getting bigger, then of course the height is getting smaller. So the question is, how is the volume changing in that instance? In the scenario that the radius is changing, the height is also changing. How is the volume changing? So we would need a relation between the volume and the radius and the height. So in this multivariable function, we would say that the volume is equal to 1 over 3 multiplied by pi r squared times height. This is the formula for the volume of a cone. It depends on two variables, the radius and the height. So we ask ourselves the question, how is the volume changing with time? And if we look at the result that we just derived, in that the rate of change of z with respect to t is equal to everything that you see on the right-hand side. What this means is that we can write the rate of change of volume with time to firstly be how volume changes with the radius multiplied by how the radius is changing with time. This is the first part of this equation, which is what you see here, dz dx, dx dt, that's dv dr, dr dt. And then the second part of the equation is how the volume is changing with the height, multiplied by how the height is changing with time. So we can now perform the derivatives on this equation. So dv dr is just simply equal to just 2r. Of course, we keep the height constants when we are taking this derivative. So we get 2 pi r h divided by 3, and dv dh is just simply equal to pi r squared over 3, because the derivative of h is just 1. Substituting all of this inside this equation, we get dv dt is equal to dv dr, which is 2 pi r h over 3 multiplied by dr dt plus pi r squared divided by 3 times dh dt. So if we were to just take some numerical values, okay? So let's just say we had the rate at which the radius was changing, and also we had the rate at which the height was changing. So let's assume that the radius is changing at a rate of something like 1.5 millimeters per second. So dr dt, so the radius is changing at 1.5 millimeters per second, and the height is changing at a rate of perhaps 6 millimeters per second. So this is getting bigger and bigger, the radius is getting bigger, and the height is getting smaller at a different rate. So we can substitute these values in, and we can actually calculate at a specific point. So at a particular radius and a particular height, given that it's changing at a specific rate, what is the rate of change of volume at a given point? Let's just say, for example, at a radius of 12 millimeters and a height of 24 millimeters. What is the rate of change of volume at this specific point? Well, we can substitute all our values in. So dv dt is equal to 2 pi 12 multiplied by 24 divided by 3. All this multiplied by dr dt, which we saw to be 1.5. And we would add to this pi r squared. Again, r is 12. Square that. Divide this by 3. And our height is decreasing. And we saw that height to be -6. Sorry, this is a -6 here. So as the radius is getting bigger, the height is getting smaller. We can imagine this practically. If we have a cone and we can adjust the size of the cone and we're able to pull the radius outward, make it bigger, we can see that the height would get smaller. Think of a tent or something like that. That would be -6. So substituting these values in and performing the calculation can easily compute this. You see that it's 288 pi and -6 times 12 squared divided by 3 times pi. That also gives you 288 pi, which is just 0. So what are we saying? What does this result mean? It means that for this cone, with its radius changing, coming outward, height going down, at a specific value, r is equal to 12, h is equal to 24, there is no change in the volume. The rate of change of volume with time is equal to 0. The amount of whatever it can hold, this cone, or what can be put inside it, will not change if the radius is changing at this rate, corresponding with that change in height. So this is an example of how we have a multivariable function, the volume, depending on the radius and the height. We're looking at it at how it's changing with time, if the radius and the height are changing, and we computed it at a specific point. We specified how the radius is changing with time, we specified how the height is changing with time, and we looked at a specific point that was r is equal to 12 and h is equal to 24, and we looked at what is the rate of change of volume at that point, and we discovered there is no change in volume at that point. In this video, we're going to be looking at implicit functions. So firstly, we want to answer the question, what is an implicit function? An implicit function is a function in which we cannot clearly see that on the left-hand side, we have all the variables, and the right-hand side, we have all the other variables. So generally, we can have y is equal to x squared, okay? So y is a function of x, y is on one side and x is on the other side. So an implicit function is different in the sense that we cannot clearly make one variable in terms of the other. So an example with this would be perhaps x squared minus xy minus y squared is equal to 0. Okay, we can see that to put all the y's on one side and all the x's on the other side, it's not going to be a very easy thing. So is it possible just by looking at this equation to find dy dx? That is, we could do it like try to find y in terms of x, express y in terms of x only, and then find dy dx. But is it possible just to find dy dx using just the function as it's written? Well, there is a way to do that, and it's to use our magic formula that we have derived thus far in the previous videos, and that is delta z is equal to day z dx times delta x plus day z day y times delta y. So you might be wondering, where on earth does the z come in now? What is the z? Why is the z here? Okay, so what we do is that we would let this entire equation equal to z. This implicit function, we would just let it equal to z, and it's equal to 0. So z is actually equal to 0, and it's equal to this implicit function. So the first thing that we can do is we can divide this equation by delta x. So if we do that, we get delta z divided by delta x equal to day z dx. Delta x over delta x is just 1, so we'll just not write it, plus delta z or day z day y multiplied by delta y over delta x. So if we now let delta x approach 0, what this means is that delta z over delta x will now approach dz dx, and delta y over delta x will approach dy dx. So if I write this formula now in terms of the derivatives, I get dz dx is equal to day z dx plus day z day y times dy dx. And what are we solving for? What do we want? Well, going back to the problem as we have stated it, we have an implicit function, and we want to find dy dx. So are we in a position to do this now? We have an equation that does contain dy dx. And here it is. So we just express this in terms of dy dx. So dy dx is equal to dz dx minus dz dx divided by dz dy. However, if we look at the original problem, we can see that we have called z to be this entire function. And what is z equal to? Z is equal to 0. Z is equal to 0. So what that means is that dz dx must equal to 0 as well. This equation that we have now derived simplifies. So dy dx is now equal to minus dz dx divided by dz dy. So back to our original problem. We had x squared minus xy minus y squared equal to 0. And all we need to do to find dy dx is to just use this formula. So the first step is to let z equal to this function. So we'll state that z is equal to x squared minus xy minus y squared. And we firstly compute dz dx. So dz dx is equal to 2x minus y. Of course, we treat y as a constant, and then we do the same with y. Dz dy is equal to minus y minus 2y. My apologies. This should be minus x. Minus x minus 2y. So the derivative of x squared is just 0. The derivative of minus xy with respect to y is just minus x, because the derivative of y is just 1. So it's minus x. That's how we got that. And minus y squared is just minus 2y. So applying this formula as we have it, yeah, dy dx is just 2x minus y put a minus in front of it, divided by minus x minus 2y. That's our answer. Well, of course, we could take minus 1 as a common factor, bring it out. So if we really wanted to do that, this would become 2x minus y divided by x plus 2y. So this is how we use our differential function. We take a function differential, and we're able to compute the derivative of that implicit function using our function differential. So this is an important application of that. In this video, we're going to look at change in variables. In the first video, we saw a simple example of how the rainfall in any given area may depend on many factors. So let's assume someone discovers in a particular area the rainfall is a function of maybe air temperature and ocean currents. currents. Later on, they discovered that both the air temperature and the ocean currents depend on their own on two other variables. Perhaps they could be wind speed and land geography. So we can perhaps assess the rate at which rainfall is going to change with respect to air temperature and currents. But would we be able to check how the rainfall will change with respect to wind speed and geography? Well, there is a method to do that, and it's about converting between different variables. So in terms of notation, we would say that z is some function of x and y. However, x is some function of two new variables, u and v, and y is also a function of u and v. So how do we now relate our derivatives to be in terms of u and v? So in other words, what we're asking is, how do we get dz du and dz dv? Okay, well, the answer to that question is to go back to our trusty relation that we have established in the previous videos. That is, delta z is equal to dz dx times delta x plus dz dy delta y. So we divide everything by delta u. So we have delta z divided by delta u equal to dz dx multiplied by delta x over delta u plus dz dy times delta y over delta u. And of course, if we extend delta u to approach 0, then all these deltas become d's. So we would get that delta z is equal, or delta z delta u is equal to dz dx times dx du plus dz dy times dy du. And the same is true of dz dv. This would equal to dz dx times dx dv plus dz dy times dy dv. So we can apply this in a very simple example, and that example would be we could have z equal to x squared minus y squared, and x is equal to r cos theta, and y is equal to r sine theta. And our question is asking us to determine dz dr as well as dz d theta. So this example is the same as the relations we have just derived now, except that instead of u and v, we have r and theta. So if we write these relations to be in terms of r and theta, what we would get is day z day r is equal to day z day x times day x day r plus day z day y times day y day r. So let's do this first before we go on to theta. So day z dx, if we look at our equation, we take y as a constant, so that becomes 0. So this is equal to 2x. Then next we look at day x day r. X is equal to r cos theta. So taking the theta to be a constant, so that remains as is, cos theta will not change. Therefore, we just find the derivative of r, and that would be 1. So our answer here would be cos theta. Doing the same for the second term, day z day y, x squared, this is a constant, that becomes 0, and the derivative of minus y squared is just minus 2y. So we have minus 2y. And day y day r, again, this is just going to be sine theta. The r derivative of r is 1. So we can substitute x and y inside this equation. X is equal to r cos theta and y is equal to r sine theta. So we can put these things inside. So that would give us 2 times r cos theta, and we already have a cos theta. So we're going to have cos theta multiplied by cos theta, and that's going to give us cos squared theta. So this becomes 2r cos squared theta. We bring the minus in front, and y is r sine theta. So in the same way, we're going to get r sine squared theta by substituting it in. It becomes minus 2r sine squared theta. So bringing this 2r in front as the common factor, we get 2r into cos squared theta minus sine squared theta. So this does look familiar. What this is, it's equal to cos of 2 theta. This is a double angle formula. So you can check that up in your high school trigonometry if you really want to. So this is going to simplify to 2r cos of 2 theta. The next part of the question, to determine day z day theta, what we would need to do is write the function differential. So that's going to be day z day x times day x day theta plus day z day y multiplied by day y day theta. So let's just remind ourselves what the function is. Z is equal to x squared minus y squared, and x is equal to r cos theta, and y is equal to r sine theta. So day z day x is again 2x, and day x day theta, well, the derivative of cos is minus sine, and r remains as it is because we're treating it as a constant here. So in brackets we would have minus r sine theta. So the second term, I'll do it on the next line. We're going to have plus. Next is day z day y. So day z day y is well, minus 2y. And day y, day theta, the derivative of sine is cos. We would have r cos theta. So now substituting all of this into this equation, we get 2 multiplied by x, which is r, and we already have an r inside this brackets here. So x is r cos theta, and we're going to be multiplying this by r sine theta. So the r times the r is going to give us r squared, and perhaps we should write the minus here as well. 2r squared sine theta and cos theta. And then the second part of the equation, we have minus 2y, so we'll write the minus again. And y is r sine theta, so we substitute that in. We get minus 2, again, r squared sine theta cos theta. So these two terms are the same, so we can just add them together. So minus 2 is minus 4. So we're left with minus 4 r squared sine theta cos theta. So again, if we remember our double angles, we would remember that sine of 2 theta is equal to 2 sine theta cos theta. So if we now substitute this inside inside our equation, we see that we're left with minus 2 r squared sine of 2 theta. So in this manner, we were able to successfully compute what day z, day r was equal to, as well as day z, day theta. So this was the objective of this video, and we were able to show this through this example. In this video, we're going to look at how to find the derivative of an inverse function, and we're going to talk about a very important quantity called the Jacobian, and how the Jacobian is used to find the derivative of an inverse function. So we could have some function u, for example, which is a multivariable function that depends on x and y. So we could say that u is equal to e to the power x multiplied by cos y. We could also have another function v. V is equal to e to the power minus x times sine of y. So thus far, you've seen that it's quite a simple matter if we wanted to determine day u, day x. Well, this is just equal to, keeping y constant, this is just cos y, the constant, times the derivative of e to the power x, which is just e to the power x. So it's quite a simple matter to determine day u, day x. So the question that we now want to answer is it possible to find the derivative of the inverse function? That is, instead of day u, day x, can we determine day x, day u? How would that even work? Well, the first inclination would be maybe to think about something along the lines of, can we somehow represent this equation in terms of x and put it in terms of u, make it somehow swap the variables around, do some algebra, or something like that and try and manipulate it and then find day x day u. It might be an option in different cases, but often it might not even work out. We would just end up with an implicit function. So there is a way to do this using the differential function or the function differential that we have been considering in the previous videos. But in any case, if we're determining day x day u, we could also determine day x day v and also day y day u and day y day v. So we will start off with the function differential as we've been expressing it thus far. We would say delta u is equal to day u day x multiplied by delta x plus day u day y times delta y. And we would do the same with v as well. We would say delta v is equal to day v day x multiplied by delta x plus delta v or day v day y times delta y. So we're now going to be performing some mathematical manipulations here. The first thing that we're going to be doing, well, before that, let's call this equation 1 and this equation 2. So what we're going to do is we're going to take equation 1 and multiply it by day v day y, and we're going to take equation 2 and multiply it by day u day y. So let's do that. Equation 1, we're going to multiply this by day v day y, and equation 2, we're going to multiply this by day u day y. So if we do that, we're going to end up with, let's just take this down. So it would be day v day y times delta u equal to day v day y times day u day x delta x plus day v day y times day u day y times delta y. And of course, we do this now with equation 2. So we're multiplying day v by day u day y. Day u day y multiplied by delta v, and that's going to equal to day u day y times day v day x times delta x plus day u day y times day v day y times delta y. So the next thing we're going to do is subtract these equations. So let's call this equation 3 and equation 4. So we're going to take equation 3 and subtract it from equation 4. So when we do this, we get day v day y times delta u minus day u day y times delta v. and this is equal to, we can take out delta x as a common factor in both these equations when we subtract it. And of course, we see that these terms cancel out. We have day v, day y, we have day v, day y, we have day u, day y, we have day u, day y, and delta y and delta y. So both of these will cancel. And what we're left with is these two terms and delta x as the common factor. So that's what we're going to write on the right-hand side. We have day u, day x multiplied by day v, day y minus day v, day x, this, and what's left is day u, day y. And of course, multiplied by delta x. So if we now solve for delta x, we make delta x the subject of the formula, as they call it. We get that delta x is equal to, well, everything that's on the left-hand side at the moment. That's day v, day y times delta u minus day u, day y times delta v. Sorry, that should be a v. Then all this is divided by well, the term that's on the right-hand side. That will be day u, day x, then day v, day y, minus day v, day x times day u, day y. Okay, so we can repeat the same thing for y. That is, instead of making delta x the subject of the formula, we make delta y the subject of the formula. So how we would do that is, instead of here we have equation 1 and equation 2, so we would swap these things around. We would multiply it by, instead of day v, day y, we would multiply it by day v, day x, and we would multiply it by day u, day x. We multiply equation 1 and 2 by those two things, and then we repeat the exact same process. And all of this would be to now express this in terms of y, sorry, delta y. So in equation 3 and 4, when we subtract it, instead of the delta y's cancelling off, what will cancel off is the delta x. So it's a simple matter to do this, and I expect you'd be able to do this part. But when we do that, we find that delta y is equal to day u, day x times delta v minus day v, day x times delta u divided by day u, day x times day v, day y minus dv dx times du dy. So looking at these two results, we see that the denominators are the same, right? So look at when we made delta x the subject of the formula. Look at the denominator. We have du dx, we have dv dy, we have dv dx, and du dy. Now looking at the denominator when we made y the subject of the formula, we have du dx, dv dy, dv dx, and du dy. So these two denominators are the same. So this denominator we can see is actually of a specific form. It's actually a determinant. So if we were to write the determinant of the denominator, we have du dx, we have dv dy, and then we have dv dx, and completing it is du dy. We can see that this is the determinant. Du dx times dv dy, this is the first term, minus dv dx times du dy, which is what the second term is. So we see that the second term is actually a determinant, and that determinant is given the name the Jacobian. Or the letter J. You just call it J. J for Jacobian. So if we carry on with our exercise and we're looking at delta x and delta y, well, we have it already in terms of delta x and delta y. And what do we want to determine? We want to determine dx du. Sorry, this does not look like a u. We want to determine dx du and dy du. So what do we need to do? Well, we take this delta x and we divide it by delta u. That's all that we're going to do. So if we divide this by delta u, we're going to divide this entire thing by delta u. So dividing the terms in the numerator by delta u divided by delta u is going to cancel off. So that it doesn't cancel off, it becomes 1. And delta v, well, if we're going to find the derivative with respect to u, it means we're keeping v constant. So this term is a constant, literally, and that means that it's going to become 0. So all that we're going to be left with is dv dy divided by the Jacobian. So let's call this equation 5. And equation 6. So the next step in this process is to take equation 5 and divide it by delta u, and then take equation 6 divided by delta v, actually both, we can divide both by delta u and delta v because we want it in terms of x and y. Okay, so it's divided by delta u and delta v. Okay, my cursor seems to have disappeared for some odd reason. Okay, we're dividing it by delta v and delta u. Fantastic, my cursor has appeared again. Wonderful. So once we do that, we then let both of these things approach 0. And following on from that, we're now able to find day x, day u, and day y, day u. So this becomes divided by delta u and also delta v. We do it both ways. And when this approaches 0, this becomes day x, day u, and day y, day u. And of course, this becomes 0, and this becomes 0 as well. Sorry, we can divide this by delta v. It depends on the variable that we're holding constant and dividing by at that moment in time. So once we do all of that, we're going to end up with the relations that day x, day u is equal to day v, day y divided by the Jacobian. Remember that entire denominator was called the Jacobian. And also day y, day u is equal to minus day v, day x divided by the Jacobian. Similarly, when we divide it by delta v, then we get the relations that day x, day v is equal to minus day u, day y. Okay, this is a u in the denominator. Divided by the Jacobian. And finally, day y, day v is equal to day u, day x divided by j. So going back to our original example that we had u is equal to e to the power x cos y, and v is equal to e to the power minus x sine y. So how do we go about finding day x, day u? Well, we'd need to find the Jacobian first, and the Jacobian, as you would recall from earlier, it's given by the determinant of day u, day x, day v, day x, day u, day y, and day v, day y. So I'll just write this again. Jacobian is equal to the determinant of day u, day x, day v, day x, day u, day y, and day v, day y. So substituting all of these things in, day u, day x, so u with respect to x, that's just going to be e to the power x cos y, because cos of y would just be a constant. So this is going to be e to the power x cos y. Then day v dx. Again, sine of y is going to be held constant, so it's going to be e to the power minus x, and the derivative of the inside function is going to be minus 1, so we have to bring a minus to the front. So it's going to be minus e to the power minus x sine y. And then day u, day y, this is going to be just a derivative of cos y, so that's going to be minus e to the power x sine y. And then lastly, day v, day y, so the derivative of sine is cos, so we're left with e to the power minus x cos of y. So the next step is to compute the actual determinant, and as you would know, we get the determinant by saying 1 times 4 minus 2 times 3, if this is 1, 2, 3, 4. So it would be e to the power x cos y multiplied by e to the power minus x cos y okay, minus, I'll write it in the next line, e to the power minus x sine y, this element, multiplied by the final element here, which is minus e to the power x sine y. So when we do that, we see that e to the power x multiplied by e to the minus x minus x is 0. So you have e to the power 0. Anything to the power 0 is 1. So we're just left with cos times cos, which is cos squared y. Minus, same thing, e to the power minus x, e to the power minus x. All this gives us is 1. Sorry, I forgot this minus here in front, so there should be a minus here as well. So it's that minus there. So the minus times the minus gives us a plus, and again this gives us 1, e to the power minus x times e to the power x. So we're left with sine squared y. And this we know is equal to cos of 2y. Double angles. So how do we go about now finding the inverse, the derivatives of the inverse functions? Okay, as written earlier, day x, day u is equal to day v, day y divided by the Jacobian. This is just simply e to the power minus x cos y divided by cos of 2y. This day v, day y is something we had determined earlier on. Day v, day y. So the rest of the differentials can be calculated in the same way. With day x, day v, equal to minus du dy divided by the Jacobian. Du dy determined earlier was e to the power x sine y. And this is divided by cos of 2y. The last two is dy du, and the formula for that is dv dy divided by the Jacobian, which is e to the power minus x sine y divided by cos of 2y, and finally dy dv is equal to du dx. Sorry, there should have been a minus here. Okay, I've put it in now. Lastly, dy dv is equal to du dx. Also, there should have been the minus sign there as well. Okay, so anyway, dy dv is du dx divided by the Jacobian, and that's equal to e to the power x cos y divided by cos of 2y. So perhaps it's interesting to get a perspective on how these relations were determined. So there was quite a bit of mathematical manipulation involved. Not to get hung up on all of the details, but it does matter in the end. So just a brief overview of what we had actually done. This was kind of a long one. We had two functions, u and v, as a function of x and y, and we want to determine the inverse derivatives. Instead of du dx, we want to determine dx du. So the first thing that we did was to write our function differentials, as we have been doing for the last few videos. Once we have done that, we multiplied these function differentials, equations 1 and 2, by dv dy and du dy. So we also needed to multiply this by du dy and dv dy, depending on what we wanted to make the subject of the formula, as we saw later on. So once we do that, we end up with equations 3 and 4. We then subtracted equations 3 and 4, and what we were left with was some of the terms cancelling out, and we left with dx du equal to dv dy and everything else. And we saw that when we made the function, we made delta y the subject of the formula, we had a common denominator. And that common denominator we called the Jacobian. And we saw that this Jacobian was actually the determinant of du dx, dv dx, du dy, and dv dy. So in a matter of perspective, the Jacobian is kind of like a transformation quantity that transforms one partial derivative into kind of its inverse. We can think of it like that, but it's not actually that, right? But it is an important quantity to determine, and it also plays quite a significant role in other aspects of multivariable calculus, which we will see later on. So anyway, once we divide delta x, delta y by delta u and delta v, and set all the limits to 0, etc., we end up with these four very important relations, which is actually the mechanism by which we determine the inverses. For example, delta x, delta u is equal to dx du, which is what we had wanted all along, is simply equal to dv dy, which is something we can easily determine, divided by the Jacobian. And the rest of the inverse functions were determined similarly using the Jacobian and some variant of the partial derivative. And then we applied all of this into a example using our original example and determining the function derivatives, or the inverse function, or the inverse derivatives like that. So this was a bit of a long one, but nevertheless, the combination of the derivation and the example is important. And I think that getting this perspective of the Jacobian and how it's used to find the inverse is quite important. In this video, we're going to be looking at stationary points, that is maximum and minimum of multivariable functions. It's a very important application of multivariable calculus. In the real world, we are always wanting to find maximum and minimum of something. If we think about in the business environment, we're always wanting to minimize costs and maximize profits. If we think about engineering, if we think about a tank, what we're wanting to do is maximize the volume of the tank, but minimize the surface area of the tank for different reasons. So it's always about finding maximum and minimum of something. And there's a specific procedure that we can follow to determine the maximum and minimum. In multivariable calculus, it's a bit more complex because we can have what's called the global maximum and the global minimum, and the local maximum and the local minimum. So what that means is, if you picture a mountain range, the Himalayas, for example, there's many mountains, but Mount Everest is the highest. So there's one point that's the true maximum, and there's one point that's the true minimum, or it could be either one of those. It could either have a maximum or a minimum, depending on the type of function that it is. So starting off with single variable calculus as a quick revision, if we have the x and y axis, and we have a random curve, we have 2 points A and B. x1 corresponds to the maximum at A, and x2 corresponds to the minimum at B. So what's true in both these instances at A and B is that the derivative dy dx, that's the first derivative, is equal to 0. So how y changes with x is 0. The tangent to the point is 0. So the tangent is just a vertical line at both A and B. So by finding the derivative and setting it to equal to 0, we're able to determine, yes, that there is a turning point, that it's a stationary point, as it's called. So how do we determine if it's a maximum or a minimum? Well, at A, we know it's a maximum because the second derivative is less than 0. And at B, we know it's a minimum because the second derivative is greater than or equal to 0. Why is this the case? Well, we can just imagine a simple illustration of a ball that's thrown into the air. We could have y as its vertical position and t the time taken. So at time 0, we throw the ball up in the air with some initial speed, and it travels, it goes up, it reaches some maximum height, and it comes away all back down, hits the ground again, and maybe bounces and then carries on like that. So what's happening here? What's happening is that at its maximum height, of course, that would correspond to its speed or its velocity that's equal to 0. So the ball stops. If we take a snapshot at this point, the ball is literally stationary. So it's a stationary point. So how do we know it's a maximum? What does that have to do with the second derivative? Well, the second derivative in this example corresponds to acceleration. Well, gravitational acceleration specifically. When we throw up the ball in the air with this initial speed, we see that the speed is reducing as it's traveling up until it's 0. So it has some initial speed when it's thrown, and it goes down until it becomes 0 at its maximum height. So the speed is reducing. In other words, it's decelerating. So the second derivative at this point is actually less than 0. It's decelerating. And then as it comes back down, what's going on? Its speed starts increasing again. In other words, it's accelerating. And then when it hits the ground, it's at a maximum acceleration. So the second derivative at the minimum point is actually greater than 0. So this is just a natural phenomenon. It's just a way of illustrating that our second derivatives is an indicator of whether it's a maximum or a minimum. This point is important in a different context in multivariable calculus. On the left-hand side, we have this little bell-shaped curve, or you can think of it that way. And at point P, we see that we have a maximum. On the right-hand side, we have the same surface inverted, and we see that point P corresponds to a minimum. So at both graphs, the x value is A and the y value is B. So this is the coordinates A and B that corresponds to the maximum here and the minimum here. So the way to think about this is if we take a random point nearby P. So that would be point Q. So Q is in the vicinity of P. So it's some h distance away from the x coordinate and some k distance away from the y coordinate. So if P is a maximum and Q is a point nearby, P will always be bigger than Q. This makes sense because P is a maximum. Maximum literally means that it is the biggest value. So anything nearby would be smaller than it. So let's write this down in terms of an expression. If we have some point that's nearby, that would be point Q, and it is some h distance away from the x coordinate and k distance away from the y coordinate, and then we subtract point P, this should be less than equal to 0. This would make sense because point P is bigger than point Q. This is point P being bigger than point Q. So we have a smaller number minus a bigger number that would be less than equal to 0. And this scenario corresponds to a maximum value. So the same analysis is applied to the graph on the right-hand side. We have a point P, point Q is nearby. Since Q is a minimum, it's the smallest value, Q would always be bigger than P. So writing that down, we have point Q again, we're subtracting it from point P, and we see that this should be greater than equal to 0, and this would correspond to a minimum. In this instance, we have a bigger number subtracted by a smaller number. That's why we get it greater than 0. Sorry. In single variable calculus, we saw that the first derivative corresponded to the tangent line, and this tangent line we saw is actually parallel to the x-axis. I've drawn it quite poorly here. Let me just draw it a bit better anyway. We see that this tangent line is actually horizontal to the x-axis, and that means that its gradient is 0. So at this maximum or minimum point, instead of a tangent line, what we have is a tangent plane. And the only way that this tangent plane would be a minimum, or rather parallel to the xy plane. Remember, the xy plane forms the base. And if we imagine we draw the base on top of this point P, you could see that it's parallel to it. So we think of a plate that's parallel to the xy plane, and that would correspond to the scenario where the first derivative with respect to x is equal to 0, and the derivative with respect to y is also equal to 0. So just as it was the case where dy dx is equal to 0, it's also the case in multivariable calculus where the derivatives with respect to all variables is equal to 0. So that's our starting point. So now our question is, how do we know if something is truly a maximum or truly a minimum? If we have our graph and we determine our derivatives, we can find stationary points. But how do we know if there is really a minimum or a maximum point at whatever point we are considering? If we can think of the mountain range example that we looked at earlier, we could find the stationary points at the tips of each of those mountains, the peak. We could find stationary points at each of the peaks. But how would we determine that actually Mount Everest is actually the true maximum value? It's the truly biggest mountain. How would we determine that? So we need a method to find the global maximum, the global minimum, or the global minimum. And what we're going to go through next is the technique of determining that. The way we'll go about doing it is writing the Taylor series for a point that's nearby the local maximum, or sorry, the maximum or the minimum. So in other words, writing the Taylor series for point Q. So it's f a plus h b plus k. And this is equal to the function value at the maximum or the minimum, that's at point P, so it would be f at AB, and then plus h times day f dx plus k times day f day y. If you need to revise the Taylor series, it's done so in a previous video. You're more than welcome to go and have a look at it. So then we look at the second order derivatives. So it starts off with 1 over 2 factorial all into h squared times the second derivative with respect to x. And remember, we have two mixed partials, so we have to have a 2 in front there because it's two of them. And then we have h times k, and of course the second derivative with respect to both variables. And then lastly, k squared times the second derivative with respect to y. And we'll have higher order terms. So we will neglect these higher order terms because it can be done so in this illustration. So we're going to take this FAB to the other side. We want to end up with this expression. So we have FA plus H B plus K, and then taking this over to the other side, minus F at AB, and this is equal to everything on the right hand side. However, we can do some simplifications here, or rather certain terms go to zero. We see that at the maximum and minimum, the first derivatives with both respect to x and y are equal to zero. So in other words, this term is equal to zero and that term is also equal to zero. So what we're left with is this part of the expression. And this is an important part of the expression. It's what we're going to use to actually determine if something is a true maximum or a true minimum. And you might wonder at this stage, how are we going to do that? Well, we're going to do a manipulation, a mathematical or algebraic manipulation of this expression that will enable us to find it. So we're going to ignore this 1 over 2 factorial because we're more interested in the signs of the derivatives. That's what's really going to influence our analysis. So we won't consider it at this stage. So the first thing that we're going to do is we're going to take out a common factor from this part of the expression. And that common factor is 1 over the second derivative with respect to x. So why we're doing this will become abundantly clear just now, but we're taking this expression and we're taking out from it 1 over the second derivative with respect to x. So when we do that, we have to rearrange this term in a particular manner. And what happens is that we have h times df squared dx squared plus k second derivative with respect to x and y. And this term is squared. So if we think about it like this, we have h squared, and this corresponds to this h squared. Then we have the second derivative squared. So that will cancel out with this second derivative being in the denominator in front of the expression. And what we'll be left with is df squared here. Then 2 times h times the second derivative with respect to x, which will cancel out again with this, times k times the mixed partials. So that will correspond to the second term in the expression on the left-hand side. However, there is a last term, which would be the second derivative, the mixed partial squared, and that is not in this expression on the left-hand side. So we would need to subtract it out from the right-hand side. But before we do that, we see that we have k squared day squared f day y on the left-hand side. So we need to also include this term on the right-hand side. So the way we'll do it is that we will add k squared. So this will correspond to this k squared. And in brackets, of course, we now need to cancel off this second derivative in the denominator. So we would write day squared f day x squared, which will cancel off with this. And what we're left with is this expression with respect to y, sorry, this second derivative with respect to y. So that's day squared f day y squared. And remember earlier, I had mentioned that when we square this last term, we'll have this mixed partial squared. So we need to subtract that out of this equation. So we have going to have that k squared, and this will correspond to this k squared here. So we'll say minus this mixed partial squared. I'll just zoom out so it can be made visible. So it is day f squared, day x, day y squared. And we close the bracket like that. So we have a fairly complicated looking expression here, and it's not really important for us. We need to keep sight of what we want. What we want is to determine what is the true maximum and the true minimum. Which mountain is truly Mount Everest? That is the question that we're trying to answer, just by determining the stationary points. And the way we do it is that we start analyzing this expression on the right-hand side. The signs of the derivatives, second derivative specifically, will enable us to determine whether it's a true maximum or a true minimum. Firstly, look at the first term in this expression on the right-hand side. Whatever the derivatives are, they are going to be squared. So regardless of what happens, this first term will be a positive number. That's the first thing to notice. Now we go on to the second term. We see that we have day squared f with respect to x and day squared f with respect to y. And we have this mixed partial also here on the right-hand side. So if we want to determine the true maximum or the true minimum, this entire expression on the right-hand side needs to be an extreme value. It needs to be either the most positive number that it can be or the most negative number that it can possibly be. So this is very important to note. So how can we make it the most positive number or the most negative number? We can make it the most positive number by this first term being positive, which it obviously will be all the time, and this second term being positive as well. And of course, this first derivative also being positive. So if this is positive and this is positive, and the first derivative is positive, then we would have maximized this entire expression. So how else now can we get the most negative number, the most negative value? Well, we can have the most negative value if firstly the term within the square brackets is also a positive number and this first derivative is a negative number. What would happen if this second term was a negative? Well, we would have a positive number, then we would take away something from that positive number that will give us a smaller number. And then the sign is determined by the derivative in front of the square brackets. So in this case here, we wouldn't get the biggest value or the smallest possible value. So this is illustrating the point that both of these terms within the square bracket must be positive numbers. So the second term here, for this second term to be a positive number, we see that both the second derivative with respect to x and the second derivative with respect to y, both of them should be of the same sign. If both are positive, then this entire second term would be a positive number, which is what we want. And if both are negative, then it would still be a positive number. But now we would have a negative derivative here, so it would become the extreme minimum. So that's a very important point. So in other words, in order to find the true maximum or the true minimum, so the true maximum or the true minimum is established, we're able to determine it when this second part of this term is positive. So that is when day squared f day x squared times day f squared day y squared is greater than day squared f dx dy. So that is a very, very important point to establish inside this entire, sorry, I forgot about the square here. Well, another way of writing this is if day squared f dx squared times day squared f with respect to y minus the mixed partial is greater than 0. This is a very important point. Perhaps it's the first important point. So the second important point is that both of these things need to be the same sign. The second derivative with respect to x and the second derivative with respect to y. So let's write that down as the second important point. So the second derivative with respect to x and the second derivative with respect to y must be more than 0. Or sorry, need to be the same sign. And lastly, for it to be a maximum or a minimum, it depends on the sign of the second derivative with respect to x. Remember that the second derivative with respect to x actually determines the sign of the whole expression. If we go back up, we see that this entire expression is actually equal to just the difference between points Q and P. And remember, points Q and P is actually whether it's a maximum or a minimum, right? So if this entire expression that we have just painstakingly derived, so if this expression is a positive number, then we have a minimum. And if it's a negative number, it's a maximum. And what we have reduced this to is the first derivative, the second derivative with respect to x. And since it has to be the same sign as y, then, well, it's the same for both of them. Both of them would be either positive or negative. So if the second derivative with respect to x and the second derivative with respect to y are greater than 0, then we have the true minimum. Or the global minimum. In the same way, if the second derivative is less than 0, then it means we have the true maximum. So what we can do at this stage is a simple basic example to illustrate all of this pieces of information. But in a nutshell, just to summarize it, we have a true maximum. So what the first thing we should do is find the first derivative with respect to both x and y. And the points at which both are 0 will tell us the stationary point. So how do we know if either of those stationary points are a true maximum or a true minimum? We determine the second derivative with respect to x and y, and we also determine the mixed partial. We apply this inequality that I've just indicated, then that will tell us if it's a true maximum or a true minimum, if this inequality is greater than 0. And then after that, we proceed to check the signs of the second derivative, and if both are positive or negative, that will tell us whether it's a true minimum or a true maximum. We'll now consider an example in which we determine the stationary values and true maximum and minimum of a given function. So we'll consider the function z is equal to x cubed minus 6xy plus y cubed. So there's a different sequence of steps that we can follow to determine the stationary values and true maximum and minimum. The first of which is to determine the derivatives with respect to x and y. That is the first derivatives. We have day z dx, and that's going to equal to 3x squared minus 6y. And we set this equal to 0. And we do the same thing with respect to y. So we have day z day y is equal to, well, derivative of x cubed is 0 since it's a constant. Then we have minus 6x plus 3y squared. And we set this to 0 as well. So we now need to solve these equations. These are simultaneous equations. And to do that, well, firstly, we'll divide this first equation by 3. So that will give us x squared minus 2y is equal to 0. And then we'll do the same thing for the other equation. We get minus 2x plus y squared is equal to 0. We can make y the subject of the formula in the first equation, and that will give us y is equal to x squared over 2. We can then substitute that in. We have minus 2x plus x squared over 2 equal to 0. That will give us minus 2x plus x to the power 4 over 4 equals to 0. So we can solve this quite easily. We multiply the whole equation by 4 and then take out x as a common factor. We get x into x cubed minus 8 is equal to 0. Solving for this, we get x is equal to 0 and x is equal to 2. We can now determine the corresponding y values. We know that y is x squared over 2. So 0 over 2 is just 0, and 2 squared over 2 is 2. 2 squared is 4. 4 divided by 2 is 2. So x equal to 0, y is equal to 0. And when x is equal to 2, y is also equal to 2. So we know that at the points 0, 0, and 2, 2, we have stationary points. So there are stationary points at 0, 0, and 2, 2. But how do we determine if they are true maximum or true minimums occurring at any one of these points? Or are they just local minimum or maximum? So to answer that question, we consider what's called the second derivative test. This is something that we had derived earlier. So use of this inequality that I am indicating here, that is the second derivative test. So we determine the second derivatives with respect to x, y, multiply them together, then subtract the mixed partial, and then we check if it's greater than 0 or less than 0. If it's greater than 0, it means that there is a true maximum or minimum occurring at that point. So we now determine the second derivatives. So the second derivative with respect to x, that will just be 6x. 3 times 2, and of course y is treated as constant. Then the second derivative with respect to y, x will disappear, and then we have derivative of 3y squared, which is 6y. And lastly, the mixed partial. That's the second derivative of z with respect to x and y. So the first derivative is now being taken with respect to y. So we have 3x squared, so this will become 0 because we're now treating y as the variable that we are differentiating. And then we have minus 6y, and the derivative of minus 6y is just minus 6. So the second partial does not depend on either x or y. So we can now apply the second derivative test. And it is to check if the second derivative with respect to x and with respect to y subtracted from the mixed partial squared is greater than 0. So the mixed partial with respect to x, we consider first point 0, 0. So at point 0, 0, because that's our first stationary point, we substitute these values inside this inequality. So we can see that if we put in x in our second derivative, 6 times 0 is just 0, and it's the same with y. 6 times 0 is 0, and of course the mixed partial doesn't depend on either one. So we would have 0 times 0 minus 6 squared. The first term is just 0, and the second term is minus 36. So what this means is that this inequality is less than 0. So it means that at point 0, 0, there is neither a true maximum or a minimum. We now apply the same for the point 2, 2. So at 2, 2, we substitute these values in. Remember that the second derivative is 6x and it's 6y. So 6 times 2 is 12, and 6 times 2 is 12 again. So we're at the point 2, 2, and just let's remind ourselves, second derivative with respect to x is 6x, so we're substituting 2 in here, so that's 6 times 2. And again, we're minusing 6 squared. So 12 times 12 is 144 minus 36. I mean, this is definitely greater than 0. So at point 2, 2, we do have a true maximum or minimum. How do we go about determining it? We just use the signs of the derivatives. You can just go back up. We see that if the second derivative with respect to x and the second derivative with respect to y are greater than 0, then we have a true minimum. And if the second derivatives are less than 0, then we have a true maximum. So now let's look at the signs of the derivative. We saw that the second derivative with respect to x was equal to 12. And this was also the case with y as well. Both are positive. What that means? It means that we have a true minimum at point 2, 2. And what is that value? All we do is we substitute 2, 2 inside our function. So this was our function, and we put in the values 2, 2. So minimum value of z is equal to x cubed, so it's 2 cubed, minus 6xy, 6 times 2 times 2, minus y cubed, that's 2 cubed. 2 cubed is 8, 6 times 2 is 12, 12 times 2 is 24, 8 minus 24 is minus 16. Minus 16, sorry, this was a plus here. Minus 16 plus 8 is minus 8. So that is our minimum value of this function. So in a nutshell, the procedure is as follows. The first step is to determine the stationary points, and the stationary points we get by finding the first derivative and setting them equal to 0, solving for x and y to determine the stationary points. And thereafter we apply the second derivative test to establish if we have true maximum or minimums, or whether we have local maximum or minimums. And if the second derivative test shows that this quantity that I'm underlining here is greater than 0, then we have a true maximum or minimum. This was the case at point 2, 2. And then we check the sign of the derivatives to determine if it's a true maximum or minimum. And if we see that they're both positive, then we have a true minimum, which is what we established. And thereafter, lastly, we find that minimum value. In this video, we're going to be talking about Lagrange multipliers. Lagrange multipliers is a technique that's used in optimization problems. What happens is that there is a function z of x and y, and we want to find the stationary values of z. Remember that the stationary values correspond to maximum and minimum values of the function. And in real life, we want to find these values because they represent some kind of optimization case. We want to optimize cost, we want to maximize profits, and that sort of thing. So in Lagrange multipliers, we're finding some kind of optimal solution or some kind of point, stationary point of z, but subject to a constraint. And that constraint is also a function of x and y. It's an implicit function specifically. To give a practical example, we could say, for instance, that we want to design and build a tank. Maybe this tank could hold water or whatever it is the case. So it's going to cost money to fabricate this tank. And this tank should also hold a specific volume of water. It should hold a certain amount of water. So what we want to do is minimize the cost of the tank. So how do we minimize cost? Well, we minimize cost by minimizing the surface area. Remember that the surface area represents the amount of material that's required to fabricate this tank. And therefore, by minimizing the surface area, we're minimizing the amount of material that we need. So minimizing cost can materially manifest by minimizing the surface area. So we could think of z as being the surface area, and this is a function that we want to minimize. So z, we could think of this as being the surface area. It's a function. And the variables, instead of x and y, we would have r and h. So r would be the radius of this tank, and h would be the height of the tank. So z is a function of r and h. We want to minimize the surface area. So one could argue that the minimum surface area is just 0. It doesn't make a lot of sense, right? I mean, if the surface area is 0, we wouldn't literally have a tank. So there must be some constraint that we need to minimize the surface area. There must be some limiting factor. And that limiting factor is the volume of the tank. We want the tank to hold a certain amount of water. So we could think of this constraint as being the volume. So in Lagrange multipliers, in these types of optimization problems, we have a function that we're minimizing and some kind of constraint that we have, which we need to consider. So we'll begin the analysis by looking at the curves of multivariable functions and then putting on top of that this constraint and then looking at the technique thereafter. So in the previous example, we just considered a function x squared plus y squared. That is the previous videos, that is. This curve or this surface was drawn in the first video in this series. So just to quickly draw it again, we have z as a function of x and y. And what this looked like was a champagne glass. Okay, it's a very poor looking champagne glass, but you get the idea. So if we take different values of z, in other words, we cut it at different values of z, and then draw that projection on the xy plane, what we would get is a series of circles. You can imagine if you're looking at this from the top, you can see a sequence of circles. I'll just redraw the graph because it just looked too bad. We have z, y, and x. Okay, I think that looked a bit better. So we can imagine that for different values of z, we would see different circles on the x-axis. So when z is equal to 0, it's just a point at the origin. Then we can have our different values of z. And this is the xy plane. So So each of these circles correspond to different values of z. They are the level curves. So this could be perhaps z is 1, we could call it z1, z2, z3, z4, etc. So this is the projection of that surface. So how now do we relate this to our constraint? Our constraint comes about as an implicit function. So we could think about some implicit function that's acting on this level curves, and it could be something like this, for instance. Maybe it's acting like that. We see that there's an intersection with one of the level curves with our constraint. We could see that if we go up, we see that if we go up, we have our surface, the function z that we're trying to minimize, and we have the constraint phi that is actually being applied to it. So just to summarize, these level curves represent the function that we're minimizing, and the red curve represents our constraint. So the intersection of one of our level curves and the constraint is our solution. And at this point, we see that they have the same gradient. So that logic is what informs our analysis thereafter. So the first step is to write our trusty differential for the function z. And we saw in the previous videos that this was dz dx times delta x plus dz dy delta y. So the first point that I think needs to be made is that this level curve corresponds to a constant value of z. So if, for example, we said z is equal to 4, perhaps z is equal to 4 there. So this function becomes x squared plus y squared is equal to 4. So this is a constant, z is a constant. And of course, the derivative of a constant is 0. There's no change because it's constant. So this delta z is 0. And then we divide this function differential by delta x. When we do that, and then of course taking delta x to approach 0, as we've done in the previous video, please look at the video on function differentials if you're feeling a bit lost. Once we do that, we find that we get something like 0 is equal to dz dx, and of course delta x divided by delta x is 1. So we have plus dz dx, sorry, dy, dy dx. So the next step is to make dy dx the subject of the formula. When that happens, what we're left with is dz dx divided by dz dy. So you might be wondering at this stage, what is the point of this? Where is this heading towards? Well, you'll see it in just a minute, the technique, how this manifests in a certain technique that will enable us to solve this optimization problem. We now repeat this function differential for the constraint. Remember that the constraint in our example with the tank, which is the volume, this is also some function of x and y, and it's an implicit function. So we could write delta phi is equal to, same thing, day phi dx times delta x plus day phi day y delta y. The key thing here to note is that I said phi is an implicit function. So it's what would happen is that we would have something like y cubed or y squared plus 7xy plus something 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 equal to 0. So please look at the video on implicit functions if you're not sure what I'm talking about. But since it's equal to 0, phi is equal to 0, it means that, again, just like as z was a constant value and it was 0, the differential is 0, it's the same with phi as well. So the same equation repeats itself with respect to phi as well. So we would get dy dx is equal to minus day phi dx divided by day phi day y. Earlier I mentioned that at the intersection of the constraint and the level curve, the gradient at that point is the same for both. So the gradient associated with this level curve and the gradient associated with this constraint, the red curve, are equal. So what we need to do is set this result to be the same equation, set both of them to be the same. So when we do that, we get dy dx is equal to minus day z dx divided by day z day y, and this is equal to minus day phi day x day phi day y. So looking at this equation, well, we can see that the numerator has to be the same as the denominator, and the numerator of the one side has to equal to the numerator of the other side, and the denominator of the one side also has to equal to the denominator of the other side. But not only just equal, they can be multiples of each other. So if I multiply either side by any number, for example 5 over 5, I'm multiplying it by 1, right? But there will be a 5 in the numerator and a 5 in the denominator, and I could do this for any number. So I could multiply it by, for example, k over k, and this equation will still hold true because I'm multiplying it by 1. What I'm saying here is that day z dx can equal to some kind of multiple of the numerator of the other side. Or the numerator of the one side, day z dx, is equal to a factor of the numerator of the other side. And the same is true of the denominator. So we could have day z day y equal to the same factor times day phi day y. So what I'm going to do next is just send this k times day phi dx to the other side. When I do that, I get day z dx minus k day phi dx equal to 0, and I get day z day y minus k day phi day y equal to 0. I can now just call k some other value, just to change it to a positive. I can call it lambda. That lambda is equal to minus k. and I can just substitute it in there. So it becomes day z dx plus lambda day phi dx is equal to 0, and day z day y plus lambda day phi day y is equal to 0. So this lambda is actually what's called the Lagrange multiplier. So what does this mean? This means that we have some equations that we can solve. We know that the constraint must be applied. So we could have the function phi x, which is a function of x and y, equal to 0. We could have three different equations. We need to solve for x, y, and lambda. So we have three equations and three unknowns. So we solve these three equations to find x, y, and lambda. I think this entire procedure is very much illustrated through an example. So we'll just look at that tank example that I was referring to earlier. So we have our tank to hold water. It has a certain radius and a certain height. We want this tank to contain 400 cubic meters of water. And we want to minimize the surface area. So there's a function that we want to minimize, and we have a constraint that we need to apply. So the question is, what is the optimum radius and height? What dimensions should this tank have such that we minimize the surface area and are able to contain 400 cubic meters of water? The first step is to set up our function, the function that we want to minimize, and that's the surface area. We have the top of the tank, the bottom of the tank, and the body of the tank. So the top and bottom of the tank are two circles, and the area of a circle is just pi r squared. So it's the area of the top plus the area of the bottom. And the surface area of the cylinder, or we use the formula for a cylinder, and that's given by 2 pi RH. And if we just simplify this, we get 2 pi r squared plus 2 pi RH. Now the volume of the tank. What is the equation for volume? So we'll call it, we know that we want it to equal to 400 meter cubed, but we need to represent it in terms of the radius and height. So we know that for a cylinder, it's equal to pi r squared times height. So remember that this must be an implicit function, and it should equal to 0, and needs to equal to 0. So that's important to notice. So how we would do it is we would represent it, for example, phi, and then we would say it's equal to pi r squared times height minus 400. So essentially 400 is equal to pi r squared times height. We just take the 400 to the other side, set it equal to 0, and call it a symbol, for example, phi. So our next step is to set up our equations. So what do we need? We need our first derivatives with respect to z and with phi. So we need to find day z, day r. If we look at it, differentiate with respect to r, we have 4 pi r plus 2 pi h. Then we find the derivative with respect to h, and that's going to equal to, well, the first term, there's no h there, so it's just going to be 0 since it's treated as a constant. Then we're left with 2 pi r. So we can also find the derivatives of phi. We find day phi, day r. So looking at this, we see that it's 2 pi rh, and the derivative of phi with respect to h is equal to pi r squared. So now that we have set up our derivatives, we can find our equations. So this is equation 1. So remember what our three equations are. We can just go back up and refer to them. So there's our equation 1 here. This is equation 1. You can think of equation 2 and equation 3. So we need to set up these two other equations. So the first equation, so the second equation, sorry, is day z day r plus lambda, the Lagrange multiplier, times day phi day r, which is equal to 0. So day z day r is given by 4 pi r plus 2 pi h. 4 pi r plus 2 pi h plus lambda times day phi day r. Day phi day r is 2 pi rh. We have 2 pi rh equal to 0. Okay, so this is equation 2. Then for the third equation, we have day z day h plus lambda day phi day h equal to 0. Day z day h, that's 2 pi r plus lambda times day phi day h. Day phi day h is pi r squared. And this is equal to 0. So from equation 3, we can simplify that a bit. So we can say that lambda times pi r squared is equal to minus 2 pi r. Then we can cancel some of the variables. We see that lambda is equal to minus 2 over r. So we now substitute, we will substitute lambda equals minus 2 over r in equation 2. So we have 4 pi r plus 2 pi h plus minus 2 over r, that's lambda, into 2 pi rh, and this is equal to 0. We're left with 4 pi r plus 2 pi h minus 4 pi h. R will cancel with r. The 2 pi h minus 4 pi h is just minus 2 pi h. So we have 4 pi r minus 2 pi h this is equal to 0. We send it to the other side. We're left with 2 pi h is equal to 4 pi r. The pi's will cancel. Divide both sides by 2, and we see that h is equal to 2r. So this is kind of an interesting result. What we're saying is that if we have a tank and we're designing this tank with the top on, and we consider it, then we should make the height to be double the radius. That will give us the optimum surface area and therefore the optimum cost to make this tank. So the last thing to do is to substitute h equals 2r into equation 1, and that will give us the actual dimensions. Sorry, that should be 2r. Substitute h equal to 2r into equation 1. Let's just remind ourselves what equation 1 is. It is just the constraint. The constraint that we said, pi r squared h is equal to 400. And remember that this is equal to 0. So we have pi r squared h minus 400 equal to 0. We substitute this 2r in. So we have pi r squared times 2r minus 400 equals to 0. And we just solve for r. We're left with 2 pi r cubed minus 400 equals to 0. So if we solve for r, we see that r is something like 4 meters. And remember that the height is equal to 2 times the radius, so this is approximately 8 meters. So this is an illustration of how we can find the dimensions of the tank that will give us the lowest costs, that is the lowest surface area to hold a certain amount of water, that's 400 cubic meters of water. So this is the method of Lagrange multipliers. To put it in a nutshell once again, the derivation of the method uses our function differentials, which we have covered in earlier videos. The principle just requires us to recognize that the function that we're minimizing has different level curves, and we look at the projection of the level curves that is on the xy plane, and then we look at our implicit function, which is the red curve, that corresponds to our constraint, and we look at the intersection of our constraint with our level curves. We see that they have the same gradient. Therefore, we write the gradient in terms of our variables, that is z and phi, and we use it in terms of our function differentials. And once we do that, and we set dy dx for both variables, that is for z and phi, then we end up with dz dx divided by dz dy equal to d phi dx divided by d phi dy. And we see that the numerators and the denominators can be factors of each other. And this factor is what is called a Lagrange multiplier. And then we create these two other equations, which is what I put an asterisk next to now. And this together with our constraint equation gives us 3 equations which we can solve for x, y, and lambda. Remember that our problem is we need to find the point, the stationary point of our function subject to this constraint. So we are solving for x and y. This is the point that is the objective of everything we're doing. And we use the example of the cylinder. We see that we want to minimize the surface area, that's our function, z. And our constraint is that it must hold a certain volume. So we create the implicit function in terms of volume, and we then create our three equations. Remember, the two equations are dependent on the derivatives. So we find the derivatives, we set up our three equations, we then solve for our three variables, that's r, h, and lambda, and then we come across our optimal solution. And our optimal solution says that when the radius is 4 meters and the height is 8 meters, then we have minimized the surface area and subject to the constraint that it can hold a certain volume. So interesting in this result was the fact that the height needed to be double the radius. In this video, we're going to be talking about exact differentials. This series of videos now is going to focus on integration of multivariable functions. Thus far, we have primarily focused on differentiation. So when integrating multivariable functions, we have to recognize if it's an exact differential. So an exact differential basically tells us if a function that is a multivariable function can be integrated or not. We have seen in the previous videos that z, which is a function of f and y, can be represented in terms of its differential, that is the function differential, being equal to dz dx times dx plus dz dy times dy. So if we are just given dz, if we are told that there is some function dz and it's represented in this form, can we integrate dz and then obtain z? How do we do this? Well, we can't just do it. We have to establish if this function dz is an exact differential. So let's just write that down as a point. We can integrate dz if it's an exact differential. So this is an important point. So what we're going to do next is recognize how we are able to see if a function is an exact differential. So our function z is equal to dz dx dx plus dz dy dy. So what we do, we call this first derivative p and this derivative with respect to y q. So we let p equal dz dx and we let q equal dz dy. So we now find the derivative of p with respect to y. So what we're going to find is dp dy is equal to dz dx. Remember that now it's a second derivative with respect to y. And we now find the first derivative, we now differentiate q with respect to x. We say dq dx is equal to second derivative of z, initially with respect to y and now with respect to x. And what do we know about mixed partials? Mixed partials are equal, right? So you can see that in probably the second video, I think, in this series. So since mixed partials are equal, we can say that dp dy is equal to dq dx. So this is how we determine if it's a function differential. We simply take p, which is dz dx, we differentiate that with respect to y, then we take dz dy, differentiate it with respect to x, and then we check if they're the same. If they are the same, then it means that it's a exact differential. We can just illustrate this in an example. So let's just write this down. So this means it's an exact differential and can be integrated. Therefore, can be integrated. So if our example says that dz is equal to 3x squared plus 4y squared dx plus 8xy dy. And now the question is, can we differentiate z? How do we differentiate z? So how we differentiate z will be the topic of the next video. But before we do that, we simply check if dz can be integrated, and we check if it's an exact differential. So we let p equal to this first part, that's 3x squared plus 4y squared, and then we find day p day y. So this is equal to 6x, sorry, it's equal to 0. We're not differentiating with respect to x, we're differentiating with respect to y. So first term is 0, and then second term is 8y, 2 times 4. Then we let q equal to 8xy, and then we find day q day x. So we treat y as a constant. So remember, it won't change. And then what do we get? We get a y. And what do we notice? We notice that day p day y is actually equal to day q day x. So this means that dz is an exact differential. So one last example. We have dz equal to 1 plus 8xy dx plus 5x squared dy. As before, we let p equal to 1 plus 8xy. We find the derivative of p with respect to y. That simply gives us 8x. Then we let q equal to 5x squared, and then we find the derivative of q with respect to x. And this gives us 10x. So what do we see? We see that day p, day y is not equal to day q, day x. So therefore, dz is not a exact differential and therefore cannot be integrated.